Glad you could join us tonight. So tonight we got a pretty busy schedule. Um, and it comes from a couple of things. It comes from not just interviewing, but it also comes from doing some SRE reviews on like things you need, and then in terms of Linux performance, also understanding some commands that you're gonna run into when it comes to troubleshooting Linux. And when I say troubleshooting Linux, I mean like, hey, I have this I have this cluster up and running, and I want to find out what's going on the cluster, or why is something running slow, or just basic troubleshooting. And these are just basic commands that you're gonna always probably run, and understand how you get there is another thing, but understanding that they even exist is the first step. So I have on the screen here some stuff, some questions, but I also in this lecture we're going to talk about nested virtualization, and then I'm going to go over some different things about virtualization and go from there. So let's get started with uh, some basic questions. And these questions are going to be things that you're going to get asked about inside of a interview. So I'm going to post these questions also on the YouTube, and also on the let me see. I'm gonna post these questions on YouTube, and I'm also gonna post these questions on the in the group. Let me see. Let me grab them all so that you can like start your own uh, search if you want to. All right. So I'm just gonna rattle these questions off, and then I'm gonna go over what I have in my notes. So one question that always comes up is, what is a kernel? What is a kernel module is really what it should say, not just a module. It should say what is a kernel module. How do you define a process in Linux? When should you use strace, ltrace, and ftrace? Um, how to find out if something is a character device or a block device? And then what is the difference between the file system ext2, ext3, ext4, and then xfs? All right. Then something that often comes up is, what's the difference between virtual memory versus physical memory? So let's work backwards. Or let me see what I have here. Yeah, memory. All right, so virtual memory and physical memory. I have here some photos. So let's grab this and go here. This may not be what I want to use. Oh, it got cut off. That sucks. So, okay, this is gonna suck. Let me see something here. Oh gosh. Let me see if this works. Mm-mm-mm. All right, that works. So let's expand this. Oh, come back. No, exit that. Let's go back and grab it. All right, I can't make it any bigger. Hopefully it's on this page. It is. But let's expand it. Okay, so in here, you see I asked these questions. What is a kernel? What is a module? What is a process? So from looking at this picture, you have to understand two things. Memory is divided up into two things. And that's what I talk about here. It's divided up into user space and kernel space. And so from looking at this picture, you see the user space, which is usually your applications. And then you see kernel space, which is by this time you've already installed the OS, and then the kernel allows you to interact with your devices. So let's break this down. So the kernel space is really where you as the admin, and sometimes in the user space, which is dealing with the applications, are going to be at, but primarily on the kernel space side, because you're going to be optimizing for better performance. All right. So, and what are you going to optimize for better performance? Are you going to optimize the hard drive, which in this case is a block device? Or are you going to optimize the CPU or the memory? And then how you're going to optimize those things is what you're going to use to determine, like, those are the how can I say it? Commands that you're going to use to optimize those things. And that's what we're looking at. All right. So you got kernel space and you have user space. User space being the application side, kernel space being the other side, meaning uh, once you got the OS installed onto the hardware, then there's a kernel that allows you to do these things. So you see on this picture, there is a device driver, right? And this gets back into that question where I say, what are modules? Well, inside the kernel, you have a list of modules that allow you to interact with the hardware. All right. So I install a new network card or a new video card. And once I get it installed and I reboot my system, I want to make sure it uses that new device that I've got in there. The first thing is first, you hope that the operating system recognizes that device. If it doesn't recognize that device, and you can think of it in a sense of in a Windows fashion, if it doesn't recognize the device, guess what you have to do? You have to install a driver. Hence, device drivers. So now I'm installing a device driver that's gonna place a module into my kernel. That's gonna allow the kernel to talk to that device. That's really what you're doing with modules. There's other things that you can do with modules in terms of, like, I want to say SSL modules. That's when you start getting into Apache. But in this case, I'm just talking device drivers and modules when interacting with the kernel. So let's go back to my notes. So memory divided into two parts: user space, kernel space. By now, you should know that the user space is what? Applications. The kernel space is, once you get the OS installed, the kernel is the thing that's driving that's the abstraction layer that's driving everything as far as the communication goes. All right. So then I say, well, the user space is set up of memory locations. And there's an actual picture out there of this for user space. All right. So let's go and look. I had downloaded these images before, but uh user space memory diagram. All right. Here. I'll go back. All right, here we go. So this often comes up, this user space versus the physical space. Let's go back to my notes. So the user space is a set of memory locations in which user processes, i.e. everything, is ran. A process is an executing instance of a program. So remember, we have a way to find out what processes are running. So PX, AUX on a system, you see these are all processes that are running, right? And when we're looking at this, remember, I'm on the system itself right now. This is what is telling me that's going on in user space. And here are the process IDs. Here's the name of the process, postfix, and here's a process ID associated with it. If you scroll up to the top of this, it'll tell you here's the user that's running it. Here's the PID that's running that particular one. Here is the CPU that particular process is taken up, and here's what is taken up in memory. All right. And then here's the command that's actually being used for that. And then you could do a man on PS, enter a breakdown, what TTY is on, what the status is, if it's a S or R, and I'll go over that in a little bit. And then the time it started right here, and you can see my time is off on this. If I do a date, you see I'm with that, but let's put it in the right time zone. Time, date, control. I think that's right. Yeah. Time zone. No. Set time zone. I think it's set time zone. And then America, New York. Uh, yeah. Let's do this with the sudo, and then let's do the date. Now we have our time correct. Let's do a PS AUX, and now you see the times are now reading properly. All right. So then we also have, okay, one of the roles of the kernel is to manage the individual user processes within this space. In other words, within the user space. So the kernel has some management it has to do. All right. So I know this is getting into the weeds, but this is good information for you to go back and review. All right. So being that the kernel has something to manage, it actually has a friend that helps it out to manage these things. It's kind of like it's related to your calendar. Well, your calendar you can list a schedule of events of things. Same way with the kernel, you have a scheduler that helps you schedule these processes. Hey, you process 24, 27. It's your turn to hop on the CPU and do your thing and grab your memory and do whatever it is you need to do. All right, once you get finished, it's going to get relinquished and process. The next process that's in this in the queue is going to do what it has to do and do its thing. How much memory you need and so forth. So it's a multitasker. So there's schedulers in this, and we're going to get to that. So in kernel space, this can be accessed by the user, me, you, the user, and we can do what we call system calls. So let's go back to that one picture. You can see here, I'm the user over here. And then when I need to do something as the user, I'm making a call to the kernel, which in turn really is making a system call to say, hey, what you gonna do? Now, what I'm allowed to do is, again, based upon permissions, but also what I'm allowed to do is also based upon the virtual file system. And so this is dependent on how you configure your file system, from ext2 to ext3 to xfs. Here they have Samba and Fuse, but really most of the time inside of Rail, since Rail 7 has been invented, it's it's XFS, and then prior to that was ext4, and prior to that was ext3, and then ext2. The differences between those are night and day. And let's give you a diagram, but I'm going to tell you. EXT2 was when we first kind of got started with file systems, and we reached the threshold of one, how the drives became larger, so we couldn't partition like whole drives. Like 1 terabyte drives, we couldn't partition those 1 terabyte drives because it couldn't configure past a certain limit. So we ended up missing space. So then they came, and it was hard to grow. So then he came out with like ext3, which added on journaling. So what ended up happening was, hey, if I lost, if a system got corrupted, say you did a manual shutdown and the system got corrupted, I then turned around and was able to use journaling to go back and pretty much give me a sequence of events of what happened and correct itself. So that's a file system check. So let's look up differences between ext2. You see ext3 and xfs. Common search there. And here, let's look at this. So you can see how far back some of these go, but BTRFS is not, I don't think Red Hat is using that. But here, this lets you know like the maximum size a file can be. Here we're getting into bytes, and ext4 only terabytes. The maximum size of volume can be, and then what type of architecture that is using. And so when I look at this, when I see hash B tree, that sounds like an algorithm to me. So and then the attributes that it may have, what kind of compression you can get. Can you get transparent compression, copy on write, snapshots? All of those things come into play. Let's see if they got another listing here. Nah, that's FAT32. That's FAT32 coming in. No, uh, they don't have any more. So I have to go back over here. But that's where you start getting the differences in the file systems here. Let's see if they got a good page. All right. Here, I give you all this one so you can have that as a reference. All right. So again, ext2 came out in 93. From here, you have a limit on the file size. ext3, this is where we start introducing journaling, where the metadata was saved. You ordered the data for you can make sure that your tracks. Remember now, we're still talking about, at this point in time, we're still talking about spindles on a drive. We're not talking SSD. We're talking about, hey, I have a rotating disk that's spinning and I have to go read where that data is at. We're still talking these spinning drives. And then ext4, that's when we start talking about SSD, and then being able to have quicker access to our data, because we don't have to worry about a drive spinning in order to go search to find out where it's at on that drive in that location. So that's what journaling allowed us to do. Is, hey, if something isn't in order, the data is not in order, then run a file system check and let journaling recorrect itself, and then come back. And then when you start getting into xfs, now we're talking about high performance. We're talking about we're walking away from the SSD drives now. Not SSD, but IDE or spinning drives. We're now talking about SSD. So that's where that comes from. This is a good list to actually look at and start. A good website to look at and actually kind of memorize some of this stuff, because these would be interview questions. So let's get back to my notes. All right. So we talked about kernel space and we talked about user space. Um, Now we're talking about, let's go down here. What does a simplification of what a kernel is? So the kernel is just really the core, the OS, um, for running and executing processes, and provides services. And so when we start talking about that storage subsystem, that's where the ext3, ext4, and xfs comes into play. All right, so virtual file system. Let's go over here to my picture that I pulled up. As you can see here, you have the virtual file system and you have the physical memory. When I say physical memory, I mean the memory sticks that you can actually pick up and touch. So that's the physical memory. And the virtual file system is what it does is it says, okay, all right, I have this process that's going to run, right? But I'm going to use virtual file system, which is just a mapping in between to the physical file system. So that's why you have this diagram here. And so as you can see in user space, we get data and text, and then pretty much in kernel space, again, kernel space is what, you know, being accessed and back down to the actual devices. I'm going to map what I can do. And then from there, I can go map into memory, actual physical memory. So one unique thing that you can do in Linux, I'm sure you can do it in Windows, but I don't know how. So in Linux, I could literally map from command line to and say I want this process or this application to run in this bank of memory. You can literally do that, right? So think about it on any given time on a server, you can have, what we call, I guess, what we consider like a bank of memory that's slower or faster. Same way with a hard drive that's slower or faster, you can do the same thing. So you can say, okay, well, I know this is my new memory in this bank. I'm gonna make sure that I run this process in that bank of memory. So when we start talking about high performance computing and we start talking about uh, as far as memory mapping, we can do that with high performance computing, and we can also do this in just regular Linux too. But you'll probably see more of that in high performance computing when people are just saying, "I want to run this in memory, but I know this memory over here is where I want to run it at." And then sometimes you just don't; you just let it go, you just let it run. Any questions so far? Because I know it's a little deep. Okay, all right. So this buffer cache, and I wanted to have this picture, but I couldn't find it. But anyway, buffer cache is the area in memory where input output requests are buffered. So remember, we have a whole bunch of data coming in at us at one point in time, but it doesn't all just go straight to the disk. It doesn't all go straight to the memory. It has a buffering technique. So I don't know if anybody have you ever pretty much had anybody ever used cut and paste. You When you cut something, it goes into a buffer, and then you pull from the buffer and paste it onto your item or wherever you're going. That's pretty much it. That's what a buffer is. So that's the same thing here. It's not the same thing, but you get the idea. All right. Let me get rid of that. All right. So the input output scheduler. Okay. So this is something I discovered this week. I didn't even know, but I'm going to show it to you. Every OS, every Linux OS, and the system that you install, there's different schedulers for Linux. I knew we had a scheduler, but I didn't know we had three different schedulers for the OS itself. So let me do something here. Let me do a df minus h SDA. So this may or may not work. Yeah, okay, here it is. So here it's telling me I have different types of schedulers that I can use. So let's see. Did I put that in here? Oh yeah, the input output scheduler is the driver that talks to the physical device. This determines how your OS will talk to the devices. So in here, I have the no-op, deadline, and CFQ scheduler. I have three different schedulers. and I can change that parameter by running this command on boot. Like when my OS boots up, I can run this command and say I want to change it to the no op or CFQ or the deadline. So what does that mean? No op meaning, hey, if I have a SAN that is attached to this file, this attached to this server, right? I want to run it in a no op because I want first in, first out. I want to get my information in as quick as I can. And notice this is for hypervisors. And I think this is probably more for type 1 hypervisors, which we're going to get into. And then the deadline here, they're talking about this is better for batches defined in first in, first out batch parameter. So this would seem like to me this will be I would use this as I'm scheduling jobs like batch jobs, and that's what and I'm on Google Cloud instance, so this is what this got it scheduled for. And then CFQ is saying like, hey, you got a lot of processes running on a disk, you may want to use CFQ as your scheduler. Now, where does this come up? So this comes up when you're doing performance tuning for a system. Say I have a system that, that may not need, that may not have a lot of processes running on it. So, do I really need for it to be looking at, to be in a CFQ mode or CFQ scheduler? Probably not. Uh, do I need to use deadline or no op? Depends. It depends on where you see that system going and how that system is working. So these are just things that you could do to tune it there. All right. So let's stop there and let's ask, do you have any questions before I go down the next road? No? All right. So what all have we covered? We covered what is a kernel, what the modules are, and what is a process. I went over what's the difference between ext2, ext3, ext4, and XFS. We also covered what virtual memory is and what physical memory is. And now I'm going to show you on the system itself what a block device is and what a character device is. An interview question would go something like, what's the difference between a block device and a character device, and how do you determine whether or not a device is a block device or a character device? Simple answer is, remember, everything in Linux is really, really simple. If you want to know if it's a block device, it probably starts with a B. If you want to know if it's a character device, it probably starts with a C. How can I find out? Let's go to /dev. Oh, that background is awful. Let me see if I could change that. Let me see. Window. Who's the guru here for the shell? How I change my colors? Okay. Oh, there you go. Let me go back. No. I just want to get rid of the wording. Grayscale? Is that a little better? In gray? Okay. We'll go with the grayscale there. Alright, so as you can see, I got the TTY, LPC. Let's look at over here. Do they have it? No. I was looking for the character and block devices. Hold on. Let me look. I know S is one. There's a directory. C the block. C ls minus f. Come on, catch up. Oh. cdo ls dev. Clear. ll minus f. Okay, here we go. That's what I was looking for. All right. So as you can see, the C shows that 9 times out of 10, that means that's a character device. And then if I scroll up to my SDA, you'll see that it's a block device. B standing for block, C standing for character. So let's go to our Google and look up character devices. What does that actually mean? Because you can actually, from command line, you can make a character device um, on your system. All right. So character device is one a device that the driver communicates sending one single character at a time, versus a block device is one which the driver communicates by sending entire blocks of data. All right, so let me give you that, which is actually true, and they give you an example. But let's go back to our example online on our thing. So SDA is an actual block device. That's our hard drive. And I know that because if I do a df minus h, if I look at this here /dev SDA1, that's my actual hard drive. And that is a block device. But if I look at what VCSA6, this USB or whatever, and when you think about USB, when you plug it in, a USB Mon zero, when you plug it in, I'm assuming at that point, if I don't format it and leave it mounted, it is sending the characters at a time. Like, but I can't mount it though. I can't mount my USB. I wonder if that's still considered a block device. If I just plug it in. But if I format it, it's a block. It becomes a block device because I put a partition on it. And once I put the partition on it, that becomes a block device. So here, the TTYs. These are the different terminals I get to open up every single time. Like I get to open up a TTY terminal, and it's just a character, and kind of makes sense, right? Because I'm just sending characters. I'm not sending blocks of data from my command line. I'm just sending characters of data. So that's the difference between a character device and a block device, and that's how you find out what a block device is and a character device is. And from the definition, they tell you C starts with is the character and V is the block, by the block. So let's get back over here. What I want to show you. All right. So now that I've shown you basically like a hierarchy and stuff, like I basically showed you. I hope this comes up. Yeah. Let's go back. I basically showed you all of this. I showed you the user space, which is usually your application. I showed you your kernel space and what's important about that kernel space, with the scheduler, with your virtual file system, when you start talking to the actual um I guess you could say, what is it called, ext3, ext4, are called, I forget off the top of my head now, file systems, the file system, when you're talking to the file systems, and then how those file systems interact and talk to the actual devices themselves using drivers. So that's kind of where that goes. And then again, they break it down to your network file system there. But still, even still, when you're talking about your network file system, you have to think that in your laptop is a NIC card. There's some type of card in there. And anytime you install a new device, even like if you plug in your USB drive or your thumb drive, it has to have a driver uh, installed on the operating system in order to know what to do with that particular device. So it's the same thing with the NIC card. Some type of driver that's installed on your system. And then we also got into like system calls. We talked about system calls. The one thing we have not talked about is commands. All right. So I'm going to skip these commands here with vmstat and mpstat, and I want to hop down to, I talked about journaling. We talked about that, but I want to talk about some strace, ltrace, and FTrace. All right. So with system calls and library calls, they're similar, but they're different. And they're different in the fact that the system calls come from the kernel themselves, the kernel itself. And you can see that here, what we talk about here, that system call, is coming from the kernel. Now, why is that important? Why is what I'm showing you important? Well, what I'm showing you is important when you start talking about how to tune something, what space you're tuning it in. If I'm tuning it in, and if I'm the admin, I'm worried about system calls. But if I am the um, application or the developer, I'm worried about library calls. All right, and so that's really the main difference between strace and ltrace. So let's look at that. So I'm gonna clear my screen. Is the gray too gray for y'all? Can you not see it? And let me make this a little bigger. Should I go back to another color? All right. So let's go back to another color. I think I was on RGB scale. Or was I on the? I don't remember. Let's see. And I no, no change. Oh, there we go. All right. Make it too light. There we go. All right. So remember the command earlier. If I wanted to find out what the partition layout is of my file system, I could just do a df minus h, right? And if I don't know what that command actually did, or what that what the options that are associated with that command, I can do a df, a man or df. All right. And in my man pages, and I can also do a df minus dash dash help, but really I prefer to go to the man pages to show you the other options that you have. So I passed the dash h parameter because I wanted to get human readable, right? But I could have done just a df, and that doesn't tell me anything, right? Has it divided up in blocks, but now I gotta do a mental conversion, and I don't want to do that because I'm lazy. I'm a sysadmin. I automate and I'm lazy. So df minus h is my go-to. But there are other commands that you can use. So one of the big things that come up um, when you have like a website and you have a whole lot of files on a website, tiny files, is called inodes. So a system can have space, but it runs out of inodes. And the inodes, if I want to know how many inodes I have here, I can pass the df minus I. What is the inodes telling us? All right, and let's just do it without it. You can see the difference there. Like, let me do df minus h again, and then let's do a df minus I, and then let's do a df minus ih. All right. So what the inodes are telling me, and this is where I've seen this happen, is I have so many small files that get written to a file system that the file system runs out of inodes, meaning every file has an inode. And if you didn't know that, that's important. So I'm gonna cd over to etc. I'm gonna do a ls minus li, and every system, every file has an inode. And you can create and this is where you start getting into like the file systems that you're going to use that can handle uh smaller files and a lot of small files. So when you start talking about inodes, you want to make sure that, especially if you're having a web server and you got maybe, and when I worked at Rackspace, this came up all the time. Hey, I have a system. I still see I have space on it, but I can't write anything else to the system, or it's acting slow or something of that nature. And 9 times out of 10, I had so many small files on there that it ran out of inodes. So this is a way, one of the ways to check with your you can check your inodes. And then another thing you can do is you can set quotas on your file system and the inodes itself too. So that's just something I wanted to show you when you start talking about that. But I did a df minus h. So when I did that, I don't know what it actually called, right? I don't know what system calls it made. So I can do an strace df minus h. Now, it just spit out a whole bunch of stuff. And this is so funny because in the Linux performance class from Sander Van Goot, I think that's his name, one of the things he talked about is like, what does this actually mean to us as we're admins? What does that actually mean to us, right? So one of the things he recommends was if you do a strace minus c. And what this tells you is, this tells you, okay, of course the command df minus h is going to run, as you can see here. But what it tells me also is the time, and it tells me the system calls that actually were ran with that particular command. So I know I had a command of stat that ran and read and open and statfs and memory map, write, memory unmap, memory protect, and so forth. And all these commands are native to the OS as well. You'll get the same thing on Ubuntu when you run this command. Like, this is just embedded in the kernel itself. But these are system calls that got ran, and it tells you the number of times that it got called. Also tells you the number of seconds and so forth. So I could do the same thing with let's do a ls minus l. All right, you can see a difference here. You can see what got called. And where's this important at is if something is getting stuck. So with the df minus h, and this is a interview question. Suppose I got a system and someone's telling me that they can't figure out what's going on with the system. In terms of, like, when I run a df minus h, it just hangs. So one thing you can find out that strace allows you to do is you can use strace, open up another terminal, use strace, and then do a df minus h. And let's do that. It's gonna work because I don't have nothing hanging. Maybe I should have wrote something that would make it hang. But you could literally walk through and find out with df minus h, with doing an strace of that, find out where it's actually hanging at. And then you can go one step further and find out, okay, well, it's hanging here, and why is it hanging there at this particular command? What is that command actually going to do? So I think next week what we would do is, under these system calls, let's look up and see what actually these system calls do. I know what stat does off the top of my head. So if I do a stat on let's see, I know etcresolve.conf is in this. Stat tells me a couple of things. It tells me the inode, where it's at, whether it's a regular file, who owns it, the last time it was accessed, the actual permissions on that file, and then because this looks like SE Linux is turned on, I can find out with a git enforce here. It's enforcing, so I know this context. This is the context that SE Linux is looking for that one. And then the access time, the modify time, and the change time. Now, all of that would change if I just open up this file resolve.conf, and I'm going to paste something there, close it. Oh, I'm not root, but that's okay. Let's look and see if this access time should have changed from showing the last time that was accessed. So let's do a stat on that. Oh, because I didn't write. Let me look. 32, 32. Yeah, it didn't change because I didn't write nothing to it. Modify. The times are still the same. So let's go back over here. Let's sudo that file. All right. So now when I do my stat, yeah, so you can see my access, my modifier, my change time all changed because I wrote to that file. And that's what that stat does. Read, when I see read, I'm thinking you're trying to literally read the file, open file, stat fs. Let's see if I can run that from command line. No stat fs. Oh, yeah. I'm not sure where stat fs is. I will have to look that up. But understanding what each one of these do. FStat, I know what that is. Close, access, BRK, I'm not sure about. Uname, I know about that. That's like you name my kernel I'm in, and then Arch PR control. I have to look that one up too. So it behooves us to look up what these actual system calls do, and I'll say that for next time we'll break all this one down. So that's a little history, or not history, or just a little similarity of what FTrace does. So let's run that same command that we had with FTrace, and let's do a df minus h on ltrace, and let's get rid of the c. Oh, it's not installed. So by default, it's not installed. So sudo yum install, or I should do a yum search because I'm not sure which program has ltrace in it. So Yum is gonna go out and search the everything for me for ltrace. So that see there's a tracks runtime library calls from dynamically linked executables. So let's do a sudo yum install ltrace -y. And remember, from what I've been gathering, strace, most sysadmins use ltrace, most application folks use. Frank, you are an application person. Do you use ltrace at all? And I know that Mike is a systems person. Do you use strace? And if you do, when do you use it? No feedback. Okay. Oh, Mike, you may still be at work. All right. So I just ran the ltrace. Okay, well, you learned something new today. All right, so I just ran the ltrace, and now you can see that this ltrace now is giving me an extensive amount of output that really means nothing to me right now. All right, let me scroll back up here. Let me do an ltrace and then pipe it over to less. All right, let's see. Come back. Quit. Let's do this. Ltrace dot out. You don't like that? Okay, put it in temp. All right, let's see. Do ls on temp. Okay, let's do a vim on ltrace dot out. All right, so of course it ran the command first, and it's not giving me. Oh, it didn't print to it. Okay, let's do this. Let's append. Still going to standard out. I wonder if there's a way to do it to a file. All right, so let's look and see. Filter config -o. All right, so let's go here. -o slash temp ltrace the out. Let me do this one again. And then let's do a ls on temp. Nothing happened. Why? Let's do dash dash output equal to /temp. We would get this solved. Nothing. What am I missing on my ltrace? So let's man on ltrace, because I want to get the top of the file. Dash output. So write the trace output to a file rather than to standard error. So while you're not going there, let's cd over the temp, and let's run this command without this. Still going. That's interesting. But as you can see, I am getting like string char, string compare, memory compare, and I'll figure out why it's doing what it's doing. But in the same fashion, that same command, I can do sudo ltrace -c df -h. Oh, sorry. Spell it right. All right. Now you can see what library calls, remember now. What library calls are being made to this particular one. And so I got mem copy, I got get intent stat vfs locale comp, just different library calls that are being made, and I'm getting at least 1,800 library calls. I am getting the time that is taking to put those calls in there. What I would like to know is this time in seconds or milliseconds? That time I would like to know. All right, so it's very similar. Shows parameters are invoked functions and system call to determine which arguments each function has. It needs external declaration of function types, but it's not telling me if that's what kind of time that is. And we'll have to dive into this next week. Somebody had something to say? No? All right. So that's your library calls. That's your strace. That's your strace and ltrace, and so FTrace. So let's look at that. Let's see if we can run the same command. Let's get rid of that C, and I may have to install FTrace. Yep. And I need to pass my sudo command. Oh, good. Let's see who has that. Yum search FTrace. Oh, trace CMD, that is correct. Now, here's where I'm not sure about, so don't quote me on this. Tracing tracing what goes on with the file system. Yes. So let's look at that command. Trace CMD, sorry. All right. So trace CMD, and I did a df -h. All right. So what you can see here, I need to pass it a command. So I want to start. I can start without recording, and it'll store it in a file called .dat, and then you can take that .dat file and look and see what's going on. And then this is let's run it. Let's see what happens. Let's do a start. Did you mean record? Sure. All right. Start does not take any commands. Okay. Oh, okay. I get you. So is it just a trace traced without it? No instances reference. Let's do a man on trace CMD. Record a live trace with a trace.dat file. Reads a trace.dat file. A command. So I'm supposed to start a record, and then I guess so from there I can start tracing the command down. So let's look up and see what if somebody has a example of a trace. Now, when I've seen tracing from an application perspective, it's open tracing, open tracing, and some other ones, Jaeger. So let me give you those. Open tracing.io, and then the latest, the other one that I've seen. Let me give you this, especially those that are in into finding out where the bottlenecks are in the application. And Jaeger is the other one. Um, Jaeger tracing. Yeah. So this guy, and I'll get you the documentation on it too. But so I looked at a YouTube, and I'll post that YouTube as well, that I followed that talked about this, because they were talking about it from CNCF, um, and they were talking about doing a call on your doing a tracing on your applications within inside the Kubernetes clusters, and within just inside clusters period. But you could see where, if you had a bottleneck that was actually coming from the database, and then do an inspection even further to see where it was coming from, like what call it was coming from in the database. Like, was it a read or a write? And so now you can go exactly to the location of where your pain points are, versus trying to figure out, well, I think it's coming from here, or I don't know if it's coming from here. But you actually got a chance to figure out whether or not you got an exact pinpoint of where that was coming from. And it was under the CNCF. I watched it. Yeah, right here. And I think this is a good one for you to watch, because this is kind of where I'm going with what I'm seeing with tracing. This is more or less taking what you see here, or what we was attempting to do. And let me grab this one and actually show you how to trace your stuff, how to trace and search for performance issues with open tracing. And I'm gonna figure out this trace CMD. I don't know, trace CMD's record. Yeah, and I think I need the instance. Let me see, trace dot that. Yeah, I gotta figure that one out. No instances reference. I gotta figure out how that command works. Once I figure that command out, I'll show you guys next week. So let's go to the main reason. Let me make sure that we got everything. Oh yeah, we forgot one other thing. The journaling. We'll get back to benchmarking and profiling next week. I want to go over that next week. I'm gonna scroll back up here. One of the big things that you do need to be aware of is vmstat, mstat, iostat. Netstat is old and SS is new, and then running a SAR. Somebody wanted to say something? No. Okay. Any questions, by the way?
Yeah, do these notes get posted anywhere after the meetup?
Yep, they do. They get posted onto the YouTube. I actually post them right down on YouTube. So if you went to our YouTube channel and looked in the comments, or not in the comment section, but like a description section, I slept all that stuff in there.
Okay, nice.
All right. So let's look at VMstat. I may have to run that as I didn't. Okay, cool. They let me run it as a user. So that's not a very good look. Let's do a man on VMstat. Why am I showing you this? Remember earlier we talked about virtual memory and physical memory. Remember now in the inside of the um, inside of the virtual memory, remember that's a mapping to what the physical memory is. All right. So let's look here. It says VMstat reports information about the process, the memory, the paging, the block IO, the traps, the disk, the CPU activity. So has anybody ever ran top?
Yep.
All right. So in top, you'll see that some information here. You'll see load average over 5 minutes. I mean, first minute, 5 minutes, and 15 minutes. Y'all see the task, the CPU, and you'll see memory information. But let's clear this and let's go and do this. Let's go back to this man on this VM stat. All right. I can do delays, or I can speed up what I can massage my information is what I'm getting at. So in here you see I have VMstat options, delay, and account. All right. So the way I just ran it without just VMstat, it's kind of it's labeled, but it's not lined up right. Right? Yeah, it's kind of hard to tell you exactly everything, but I'm gonna walk through it real quick. So it tells me again my memory. If we just look in here, let me go this way and straight down, we see that I got swapped, free, my buffer, and then my cache. Right. Next one I got and then that's telling me what is swapped. And then remember I got swap here, but this right here is from the system input and system output. And then I got hold on. Then I got input and output, and then I have system, and then I got CPU. Now, the reason why I showed you this is because you see this stuff right here is actually shown here in top, where you start talking about uh, user space, system space. I forget what NI is. The ID is that no, and then this is the hardware interrupt, the wait, the system interrupt. I forget what the ST is off the top of my head. I have to look it up again. I'm supposed to know all this off the top of my head. I don't remember. Don't hold me accountable for that. Let's go man on top right quick. And let's scroll down. Come on, come on, come on. CPU. All right, here we go. Sorry. All right, all right, all right. No, that one's yeah, it was CPU. The idle process. I just want to get what the different ones are. And I always come through here. Upload to and remember, oh yeah, here we go, here we go, here we go. All right, so user system nice idle uh wait IO wait. This is the hardware interrupt. Now when you're experiencing hardware interrupts, there's something to look out for. Your software interrupt and ST stolen time. Gotta remember that. Why am I showing you this? For a couple of reasons. One, it's an interview question. Two, is how
Uh-huh.
you check performance. Three, what'd you say?
Oh, sorry.
Oh no, you're fine. One is another one is how you check performance. But if you didn't know, if you were in an interview and somebody asked you how would you check performance on a system, what top is one, but another one is vmstat that's going to give you that virtual memory information. So I could do, I'm going to do back to vmstat here for a reason. All right, so I can pass different parameters, and I'm gonna break this down. Probably won't have enough time to break it down because I still want to get to the nested virtualization, and I'll tell you why with that as well too. So here it breaks down what each field is. All right, so R, runnable processes; B, the number of processes of uninterruptible sleep; swapped. Remember virtual memory now. Free is the idle memory. Buffers, cache, inactive memory, active. Again, swap. We're talking about disk information here. And then SO memory swap to disk. All right. And then we start talking about the blocks of information. Remember, there's a difference between block devices and character devices. We're talking blocks here, and then your system, and then again the CPU, and then they start going into like the different disk modes and the writes. So I would thoroughly go over these things. All right, but with that, you could do vmstat dash dash help, and it gives you the options. Let's do active memory, and let's just do dash A. So it's just going to show me uh, the active and inactive memory. But if I want to look at stats, I can just do dash S. Now that's giving me something totally different. All right, and we should take some time and go over all these. I just want to mention them to you because I have them down. I just want you to be aware of them. All right, so then there's this MP stat. All right, so let's do a man on MP stat. All right, MP stat command writes output activities for each available processor. Well, I don't know how many processors I have, right? So let's do an LSCPU. As I got one CPU, but this is how I can find out how many processors that I have on my machine. So now if I do an mstat for that CPU, I'm getting what's going on with that actual CPU. Is there a wait? Is it stealing time? Is time being stolen? It's idle. Hold on, clear that right quick, and then run that again. Um, IRQ, IO wait, nice. User space is giving me everything about that particular uh, that one single ah, that one single CPU. I'm sure you could probably break it down by a CPU. So let's do a man on MP stat. Let's see. Yeah. So you could give it a CPU there, right? So you can pass the CPU, and it goes and explains all of that. Now the next one is IO stat. You kind of got a feeling for IO stat, what that means. Again, this is my device, my block device, and these are my read and writes uh, that I'm getting for this device. A TPS, I forget what the TPS is. Let's go, man, on IO stat and TPS. TPS. Indicate the number of transfers per second that were used on the device. All right, and then remember before we used to do netstat in Rail 7, they got rid of that because this is a cloud image by default. It is still in there, but you could do a netstat dash PANT, gives you all the ports that are open on a TCP connection. So if you don't know um, if you're not sure, you can do netstat net stat dash dash help, and then in here I use PANT programs, A is always all, N, lowercase n, numeric, and then P for PANT, T for TCP. I can back out of that and just do U, and it's going to give me everything on the UDP, as you can see over here on the left hand side. When I put the T back and I put a PUNT back in there, you'll see I'm getting the connections on TCP and UDP. What I'm not getting is I'm not getting information resolved. So I think that's the R command. Um, Let me double check. Man, next step should be resolving my. Um, I wanted to resolve my actual uh, IP addresses. So let me see, what is that resolve? Resolve. I have to look it up again, but you can set it up where it will resolve the IP addresses. So that's cool. All right, and then SAR. All right, so I forget when SAR came out. I think it came out in Red Hat 5, maybe 6. So I can run, let me see. Can I do SAR? Yeah. All right, so man on SAR. All right, so SAR gives me counters in the operating system, like an accounting system. Um, what I've also seen SAR run is giving me uh, a report on stuff. And this is not a good explanation in here. Let's go here. SAR command Linux. Yeah, I know it's CPU utilization, but it's a little bit more. Here we go. Render. All right. I'll give you this link because this is a little better. All right. So collect the CPU usage, individual CPU stats, memory used and available swap space, context switch statics. Context switching is a number one question when it comes to interviews, especially those that are going out for SRE and when you're talking about um, Linux performance. So, context switching. One of the questions is, what is context switching? What is context switching in Linux? What does it do? How how can you tell me what it does and how can I find out? So these are things that often come up. All right, so context switching, also referred to as a process switch or task switch. So basically, context switching is I have a process that's running, and then I switch over to another process, and I'm able to track that that switching of those processes. And if you really think about it, and I could be wrong on this all to me sounds like a scheduler as well. Something getting scheduled onto the stack, and then a process does its thing, and there may be some type of, hey, you can only use this for so much amount of time, and then you come over. And I'm pretty correct here. So context switches can occur only in the kernel mode. Kernel mode is the mode of the CPU in which only the kernel runs and provides access to all memory locations and all other system resources. Pretty much spot on there. And again, here we go with system calls. I'll send you this link instead of cutting and pasting that. And I'll grab these links. I won't close out on my thing. I'll grab these links and I'll post that too. Any questions so far? Yeah. All right. So we went over all this information in here. I did not go over the sys file system. I still got to go over proc. I still have tuning on the hard drives. We didn't get to that. ext4, Mentioned about journaling, tracing. Again, this is closer to the application. Again, on user space, application and tracing. So we kind of touched on some tracing, but we want to do open tracing, and we should look at those. And I'll try to find other stuff. Map is another question. What does map allow you to do? The answer is I can now take a I can take a program and map it into memory in order for it to run in a specified memory location that I have declared. That is where that comes into play. Another question that comes up all the time in some of the interviews is, uh, and this is kind of lead into what we're getting into. How does VMware vMotion work? And I was like, man, there was like, I was kind of stumped for a minute. Then I had to think about it. I know that the application from so the way VMware or vMotion works is share storage between two hosts, and I should say virtualized hosts. And so what ends up happening with vMotion is I migrate one VM to another one VM from one host to another host. But what ends up happening is that particular VM gets pushed into memory, and basically that memory is a bitmap of what it actually looked like on one side to another side. And so it gets pushed into a bitmap. And then once, depending on how you have things set up, once you get it pushed into memory and then pulled back down on the other side, it shouldn't be seen, it shouldn't affect the user, but um, you can either set it up where it turns itself off on the other end, or you can set it up where it just gets put over onto the other side, and then you go and manually turn it on from there. So just a FYI. And then one of the questions that usually gets followed up by that is, what is a bitmap? So a lot of information here, but I want you to be aware of these things. All right. So, yeah, Intel. I don't know if this is going to be a good one for you. Yeah, that ain't it. I'll try to find it. I'll make note of it and write it down in my notes. Define what a bitmap is and show in virtualization. All right. All right. As you can see, I got next week profiling and benchmarks. All right. Any questions before we finna dive into this uh, next topic of nested virtualization? All right. So let's give some background. Virtualization type 1 and type 2. Uh, Virtualization type 1 and type 2. Where's this come into play? Well, this comes into play, one, another interview question. Two, understanding what type 1 and type 2 are. I'm going to give you this link, but I also already have some examples. So virtualization type 1 and type 2. So type 1, you'll mostly find that with VMware, meaning like I have a bare metal machine, and then I'm going to take VMware and throw it on top of that, and VMware is like considered my OS per se. It's not I don't want to call it an OS. I just want to it I want to call it like an expanded kernel, because now I can interact directly with the hardware of that particular machine. And when I say interact with that hardware is I install VMware on top of there, or I install Hyper-V, and I have access to the actual devices themselves, from the network to the actual um, device driver. I mean, not device driver, but the network, the physical storage, the CPUs, the memory, everything about that. And if I have the correct optimized virtualization kit, and I've optimized my VM, I mean my machine, I can inside of VMware we can access stuff what we call pass through. And what that will allow me to do is, instead of having the virtualized VMware manage everything, I could just pass that on to directly to the VM that I create. So it's a lot of things that go in behind it. I will always encourage people to go look up VMware and just see how it works, because it's still huge in the community and so forth. All right, so let me quit out of my Slack because I keep getting pinged here. Um, so let's look at uh, type 2. So type 2, I think everyone is probably a little bit more familiar with VirtualBox, VMware Fusion, VMware Workstation. Those things are all great if you have your Mac laptop or your Windows laptop or what have you, and you just want to have a virtualized environment. Um, Before Docker came out, that's what it was. But now you got Docker and Vagrant, but you still need some type of virtualization there. But you can still log into a container on your machine. But we won't get into all of that. All right, nested virtualization. Why did I bring this topic up and what's so important about it? And I'll expand on it next week as well. Um, the big topic about it is, and let's get to this link um, here. All right, so I was looking for a way to say, like, how can we use cloud distribution in order to study for our RACSA class, or how can we set up um how can we set up let me see, you said it said page not found. All right, let me copy the link again. How can we set up ourselves to have an environment where, say, I am at work and I need to make a migration of a KVM instances to Google Cloud, but I don't want to convert those instances over to Google Cloud's container engine. I mean GCE instance engine or container engine. I don't want to convert over to EC2. What I can do is leave my machines the way they are in KVM and literally forklift them from my local on-prem stuff directly into the cloud. And that's where that comes into play. And let me give you this link, and Fred, I haven't forgot about the other one. This came up for me and it went away. And I gotta figure out which one that one is. Is it that one? No. Oh, here you go. All right. So basically, there is a way in Google Cloud, in Azure Cloud, and in AWS. And I want to go over all three of those. Won't be tonight, but I want to go over all three of those so you can understand how you can walk into a situation where somebody may be running KVM on an OpenStack cluster on-prem and they want to migrate it to Azure, or they want to migrate to Google Cloud or what have you, and you can do that migration pretty much as a forklift. So here they talk about what does that look like. So basically, from the perspective of Google Cloud, um, Amazon, and Azure, this is what it looks like. It looks like, hey, and if you don't know, Google and um, Amazon both run KVM as their hypervisor. So basically, what we're doing is putting a hypervisor on top of a hypervisor, and that's what this is explaining. So the hypervisor that they have is they're running is KVM, and that's considered they considered that we got the host, and then on top of that host, we have a hypervisor, which is the KVM. And then what we're gonna come and do is we're gonna put another hypervisor on top of that hypervisor, and then on top of that hypervisor, I can run multiple VMs within that. So I don't know if anyone has ever used KVM. So if you have a Linux desktop at home, you can install Red Hat Linux and then install KVM and use Versh. But suppose I don't have a machine at home and I want to study this for, say, my exam. Well, here's a way you can do that. And that's why I introduced all the other stuff for performance and tuning and hacking and trying to figure out what's wrong. So now you got those tools. So that way, when you come here and you start trying to figure this out, you can figure it out. So that's what this is. So I went through these steps. And I'll go over this with you. They talk about nested virtualization. They talk about the processes that you can use, and then they also talk about they're all KVM based. And then there was like Windows doesn't support it, so don't look for don't use this with the Windows instances. But you have to walk through these commands, which I've already done, and enable nested virtualization on your Google Cloud. And the instance that I have been using, I did this earlier. So basically, you're gonna pass this command here with this here. So you're gonna create an image, and I'm just gonna talk this out, and then I'll go back and show it to you. um, G Cloud, compute images. You're gonna just create an image, so you can take whatever image that you may have already in Google Cloud, or you can create one, or you can use one of theirs and say, okay, well, I want to create something called a nested image, but the disk source I want to use is this particular disk, put it in this particular zone, and then license this for to enable VMX. And then once you enable VMX, you go into Google Cloud from command line or inside of Google Cloud Console, and you say, "Well, I want to create an instance based off that particular nested image." And then once you get done, you can SSH to it, and then you can go to here and then do CPU info and see that it works. So I'm on the instance now. I'm just gonna grab this. I went through these steps already, and let's clear this out. And you can see I get a 1. They say anything that's a non-zero. So now my next steps is update the instance, and I'm not inside of. I don't think I. Oh well, let's see. Let's see if these work. I don't think I chose. I don't think this is a CentOS. I don't think this is a. I know it's not. Yeah, this is a what you call it. So let's sudo yum update dash y, and then let's sudo yum install. Let's do a search for KVM. It may be I may have to do Versh, but let's find out. So it's gonna do its thing, do its update, and then I'm gonna search for KVM. But in here, they use QEM KVM, and then they download the image, and then basically they run screen just to give you the way to record there, and then they uh, start with a nested VM when prompted. So now you're starting to do your nested VM with a QCal image. They give you a size there. You get a HDA, and then they also run. They enable KVM, and then test your external access, and then you're pretty much done. So here they start doing like I guess if you want your images to talk to each other or your instances to talk to each other, you can set up a private bridge between the two. and we're gonna go over this all next week. We're not gonna do it tonight, but you set up your private bridge, which is what you would have to do if you were running on Red Hat Linux, and then they got another screen session, so forth. Looks like they're setting up another VM, and then now the two VMs should be able to talk to each other, and then you should be able to access from outside. So we're gonna go through this next week. I'm gonna knock it all out, and then what I should do is make a script for you so you can run all this stuff here. But I thought it was just a cool way so that you could study. Let's see where we're at on my. Yeah, it's doing this update. 973 packages. Yeah, that's gonna be a minute. But I say all that to say I'm gonna post this video. But do you have any questions? Because we're gonna go over this next week, and then I want to try to go over the one from doing this in AWS, and then what we should be able to do is we should be able to take a instance, a KVM instance that we have that we created, excuse me, and push that up to and migrate that over to our cloud with and onto that particular uh host. I mean, it only have to be like 1 gig, but and migrate it over directly to our host that has KVM initiated, and we should be able to bring it right on up. And let me go over here because I'm gonna post these online too. But I think this one is one of the best ones that actually tell you the one from the new stack. Where'd it go? The new stack one has a good breakdown of this. And it came out, I think, in December of 2017. And they have a good breakdown on when you would use this. Yeah. So they talk about Microsoft Azure, again, Google Compute Image, and then Amazon. And like I said before, Amazon make the switch from Zen to KVM. And they talk about lift, shift, and append. Like talk about like, hey, I have all these KVMs on premise, but now I want to put them inside of Google Cloud, but I don't want to have to convert them over. I can just forklift and put them out there. So that's what this comes into play. But you got to set up, the back end, uh, the networking, the bridging. There's your security groups and firewalls and so forth. You got to set all that up. But it's better than having to recreate the wheel if you don't have everything set up as infrastructure as code or something like that. And I'm gonna stop recording too.